Hello guys, this is Atomic Scientist, and today I'm going to be talking about part 1 of the closed nuclear fuel cycle. And just so you know, I'm not pulling this stuff out of my butt. I'm getting a certificate of basically approval in nuclear energy from the University of Pittsburgh. So I'm not pulling this stuff out of my butt. So let's begin. The first step in the nuclear fuel cycle is getting your uranium. So let's talk about the uranium atom for a little bit. There is two isotopes of uranium: uranium-238 and uranium-235. Uranium-235 is the most common, or uranium-238, not uranium-235. Uranium-238 is the most common isotope. It doesn't really do much. It's just really heavy, and it's weakly radioactive. And I'll be doing videos on radioactivity in the future. So let's talk about the most common uranium-238. Its counterpart is uranium-235, which is what we're going to be focusing on. I'll just talk about uranium-238 just so we know what it is. Uranium-238 is it's an isotope of uranium that is heavier than uranium-235, very slightly heavier. It's got a few extra neutrons than uranium-235. So it's slightly heavier. It doesn't do well in a fission reactor. It doesn't really do well in a nuclear reactor or in a nuclear weapon. I'll do a video on nuclear weapons later in the future. So what you want is uranium-235, and uranium-238 doesn't really do much. It's heavy, it's radioactive, weakly radioactive, weak alpha emitter. It emits alpha particles, helium nuclei with no neutrons, or helium nuclei with no electrons. So now that we talked about uranium-235 a little bit, or uranium-238 a little bit, let's talk about the main element, uranium-235. Uranium-235 is an isotope of uranium that is very fissile. It does very well in a fission reactor. A fission reactor shoots neutrons at it. The uranium-235 splits in half, creating elements that have very short half-lives. Some don't even have 1 second half-lives. The longest half-life is about directly from the fuel cycle is around 13 days. So, uranium-235. So what you need is, in the first step, is to actually find and mine uranium. So, here's a fun fact. Uranium is actually more common, or 40 times more common than silver. About as common as tin. And tin is somewhat common. Uranium is 40 times more common than silver. You have more chance to find uranium than silver. So let's move on. So once you find the uranium, there's conventional mining, open pit, i.e. open pit mining, and then there's in situ leaching mining. Let's get conventional mining out of the way first. Conventional mining is just digging to the uranium ore, which uranium decays into some atoms of uranium decay into radon. A lot of the uranium decays into thorium. Some uranium decays into radon, which is a gas, and it's not too good for you. So so open pit mining is just digging and blasting away. That devastates a landscape and probably pollutes groundwater or water from somewhere else, near the mine probably. In situ leaching is you dig down to the uranium ore, possibly past it. I would think past it. didn't really talk much about in situ leaching and how far you go. You dig to the uranium ore. You have pipes filled with water, which go mix with uranium, which carry it back up. You suck the water back up, then you store it to be processed. Once you have the ore, or the ore. Once you have the ore, you can crush it, refine it, get the uranium out, and then you have yellow cake, which is refined uranium ore. It's not enriched yet. It's just uranium ore. So what do we do with the rest of the rock, the ore? Well, we can refine it to get all the other elements out of it to be used for something else. So it's not really gone to waste. We don't just throw it away. So there's mining, an overview of mining for you. Now we go down to, so once you have your yellow cake, you can go to a facility that turns it into a gas, uranium hexafluoride. Uranium hexafluoride has a gas at room temperature, and then you send that to an enrichment facility with centrifuges. Probably the newest way, one of the newest ways is lasers. I'll talk about the enrichment more specifically in other videos. So let's just do the centrifuge. You spin it really, really quickly, and uranium-238 is slightly heavier than uranium-235. Uranium-238 goes around the edges, uranium-235 collects around the center. The center is fed into another centrifuge, which spins it. The center is fed with more centrifuges, and so on and so forth. So you literally need thousands of centrifuges to have adequate uranium-235 concentration. I'll just call it U-235. So once you actually enriched your uranium, it's still a gas, so you need to capture the gas. Then you need to send it to a fuel fabrication facility that fabricates it into little fuel pellets. One fuel pellet that is 0.2 centimeters wide and probably tall, it's just a little cylinder, provides enough energy, or the equivalent energy as 2,000 pounds of coal. And remember, the uranium is a weak alpha emitter. It emits alpha particles. Alpha particles are helium nuclei with no electrons. So that's quite a lot of energy from a teeny little space. And I'm not going to say I'm pro or against it. I might come out and say something. Actually, leave in the comments below what you think about nuclear energy. Is it good? Is it a good thing, or do you think we should improve on it? Just is it overall we should work on it, or should we just completely ditch it? Considering Chernobyl, 3 Mile Island, Fukushima. I'll do a video on Fukushima. So once you have uranium hexafluoride, you go to a fuel fabrication facility. It condenses the uranium hexafluoride into a little pellet. Then it goes into the reactor as fuel rods. And then it's being used for power. And this is a brief overview of quite a bit of the nuclear fuel cycle. This is the closed one, the one that most other countries use. The only country that does not use it is thanks to good old Jimmy Carter, when India got our plutonium to make a bomb. I'll talk about plutonium too. And this is Atomic Scientist with the closed nuclear fuel cycle. We left off at the reactor, and I'll see you in the next video. So, goodbye. Signing off.